Hello, my name is Peter Deli, and in this screencast I will present FUZPAG, a fuzzy control packet aggregation scheme for wireless mesh networks. FUZPAG is a joint project between Karlsruhe University and Deutsche Telekom Laboratories in Berlin. In this screencast, I will first introduce wireless mesh networks and explain the IEEE 8.11 MAC layer, which is used in most mesh networks. I will explain what is the problem when transmitting small packets using that MAC layer. I will propose a solution and give several demonstrations of the performance of this solution. So, what are wireless mesh networks? Let me explain that by an example that you all know. Consider you have a classical wireless LAN. In a wireless LAN, you typically have stations. Mark that here. You have stations and access points. And if a station, for example a notebook, would like to connect to the internet, it associates with an access point and wirelessly transmits data to the access point, and the access point forwards the data to the internet. The problem about this setup is, if the station moves further away, the wireless link will break and no more access to the internet is possible. One potential remedy for this problem are wireless mesh networks. In wireless mesh networks, you replace the access points with wireless mesh routers. Wireless mesh routers wirelessly relay data on behalf of other mesh routers or clients. Let me show that by an example again. Consider one mesh client here that would like to transmit data to the internet. It first wirelessly transmits data to the first mesh router, which wirelessly forwards it to the second mesh router, which again wirelessly forwards it to the mesh gateway and then to the internet. Similarly, you can transfer data within the mesh network, for example from this client to this client. Wireless mesh networks are typically self-configuring, self-organizing, and self-healing. The distributed nature of wireless mesh networks usually allows no central control instance. Today, wireless mesh networks are, for example, used for broadband access in rural areas or industrial applications. Most of today's wireless mesh networks are based on the IEEE 8.11 standard. IEEE 8.2.11 uses CSMA-CA as a MAC layer. When transmitting small packets, which can be found in multimedia applications such as voice over IP or online gaming, the overhead is high. Consider the example in the two pictures here. When transmitting a small packet with only 28 bytes, the fraction of time that will be used for transmitting the payload, which is indicated by the green portion here, is very low. However, when transmitting a larger packet with 2304 bytes, the fraction of time that is used for the payload here is much higher. When transmitting small packets, the efficiency is low and thus the capacity is low. For example, in a wireless mesh network that consists of 3 wireless hubs and a physical layer operated at 54 megabits per second, you can only transmit about 20 concurrent voice over IP calls. I would like to demo that a bit more in detail. For the demo, I first want to explain our demo setup, and then we'll show some demonstration of the impact of different packet sizes. In our setup, we have 5 mesh nodes which are deployed in a lab room at Deutsche Telekom Laboratories in Berlin, shown in this picture here. The wireless links are indicated by the arrows. The logical topology of the wireless mesh network is shown here. There is an internet gateway, node 225, and then several wireless hubs, and we have 2 wireless mesh routers here, 205 and 245, which can be used for generating traffic. Please note that in this mesh network, we use multiple radios in each mesh router and allow to use different channels. For example, on this link we use channel 140 and on this link we use channel 36. Using different channels allows us to transmit simultaneously and increase the capacity. In the demo, I would like to show what is the impact of different packet sizes. For this demonstration, I will generate UDP traffic at node 215 and send it to node 225. The UDP traffic is backlogged on node 215, meaning that we have always packets to send. The throughput here is measured and displayed live. Let's start the demo. Let's start the demo by first setting up the network. This takes a few seconds. We need to do some network configuration and start MGen, which we use for generating the traffic. And in a few seconds you will see two windows popping up. The one shows the demo events. That is a printout of what is just happening. So here we are disabling the aggregation for this test. And the second window shows the throughput which we measure live. So let's wait a second here. So here you can see the throughput if we send packets with 100 bytes length. The throughput is around 800 to 900 kilobits per second. In the next step, we use packet size of 500 bytes instead. You can see that the throughput here is around 4 megabits per second. So roughly 4 times what we got before. And in the last step, we will use packets with 2000 bytes length. Here the throughput is around 12 megabits per second. So as you can see, increasing the packet size has dramatic impact on the network throughput. We now know that transmitting large packets can increase our throughput. We can utilize that by using packet aggregation. The basic idea of packet aggregation is to concatenate several small packets to a larger packet and transmit that large packet as it was a real large packet. In the picture on this slide, you can see a typical packet aggregation scheme. Packets are generated locally or coming in from other nodes, and the sender would like to forward them. Prior to sending, the packets are stored in an aggregation queue, shown here. Right before sending, the packets are concatenated and transmitted as it was one large packet. By doing that, the overhead is reduced. At the receiver, a deaggregation module deaggregates the packets, and the packets are further processed as they were normal packets. Please note that at the aggregation queue, we need to delay packets in order to have enough packets available for aggregation. The time that a packet is artificially delayed in the aggregation queue is called aggregation delay. When selecting the aggregation delay, there is a trade-off that needs to be considered. Having a large aggregation delay gives us many aggregation opportunities and leads to large packets. This gives a good efficiency. However, delaying the packets for too long in the aggregation queue leads to a large end-to-end delay and has adverse effects on the quality of multimedia services such as voice over IP. So the key here is really to find an aggregation delay which gives us a good efficiency but also a low end-to-end latency. I would like to demonstrate that with a simple example. In this example, node 225 pings node 215. The ping gives us the round trip time, and this is an indicator of the quality that voice conversation will have when being transmitted there. In this demo, we first set the aggregation delay to 20 milliseconds. In the top window, you can see the round-trip time as measured by ping. The round-trip time is around 40 milliseconds. This is the result of the 2 times 20 milliseconds we add when aggregating the packet at the sender and when the ping packet is replied. In the next step, we set down the aggregation delay to 0.1 milliseconds. You can see the round-trip time immediately goes down and is now just as if we had no aggregation. From this demo you saw that the aggregation delay has a big impact on the round-trip time or the end-to-end latency.